Hey everyone, this is the final lesson in the exponential and logarithm unit, which is all about logarithmic regression. So just like we have done for all of our polynomial functions, and we did it in this unit with our exponential functions, we can also do regression for logarithmic functions. And the way that we do it is going to be the same thing. We're still going to use Desmos, make a table of values. Since I made my previous my previous regression video, I did find that there is an easier way to find regression on Desmos. So we're going to go over that as well. So we are just going to take a look at an example here, and there are a bunch of questions that go with it. So let's just jump right into it. It says, the data below shows the average growth rate of 12 weeping Hagen cherry trees, I don't know if that's right or not, planted in Washington, D.C. At the time of planting, the trees were 1 year old and were all 6 feet in height. And we have this table here of the age as it goes, so year by year, as well as the average height of the trees. So the first thing we're going to do is determine the equation of the regression function, and we're going to graph it on the graph right here. Okay, so on Desmos, we're going to switch over here. And what we're going to do is we're going to click the plus to add a table. We've done this many times before. Let's go ahead and enter our x values. Very easy to do because they are just going up by 1. My y values I'm going to pay a little bit more attention to. So 13, 15, 16.5, 17.5, 18.5, 19, 19.5, 19.7, and 19.8. And the reason why we can tell just from looking at the table of values that this is a logarithmic function is because you can see that my height was really increasing until we got to a certain point, and it just kind of stopped increasing by, increasing by smaller and smaller margins. So once we get into like 10 and 11 years old, they're not even really growing that much in height. Anyways, that is my table of values. I'm just going to zoom out a little bit just so we can see all of the points. And now the new way that I've discovered to find regression is if you click on this like branch looking thing here on the left, it says add regression. So we can just click on that and it brings this drop down menu where we can choose what kind of regression we want. Now the one thing I want to point out is we are doing logarithmic regression. We are not doing logistic regression. Those are two completely different things. So even though we're talking about log functions, make sure you know that we're doing logarithmic. So make sure you're clicking on the right thing. So when we click on that, it does bring up the equation here. Y equals 6.099 plus 6.108 ln x. And when you write your equations, make sure that you're rounding to at least 2 decimal points. So make sure you have at least 2 numbers after the decimal point. If you want to write more, you are more than welcome to write more. So I'm going to go ahead and write that down. And sorry, I'm clicked off of there, but I realize I do need to write it down. So I'll switch back to the notes in a moment. So 6.09934 plus 6.10818 ln of x. That's another thing I want to point out here is when we do logarithmic regression, it gives us the natural log regression, which is what we are looking for. So ln is for natural log. It is the inverse of the exponential function e to the power of x. We talked about that in the last lesson. And let's just switch back to the notes. So I have my equation written here. So if we go to graph our data, we don't really have a lot of space here, to be honest. So let's just kind of graph it as best as we can, as many points as we can, and see if we can kind of space this out as best as we can as well. So at 1 year, we have 6. At 2 years, we have 9.5. 3 is 13. 4 is 15. And if we keep going, we kind of get that general shape. Now, if we were to graph the line as well, just pay close attention to where your x-intercept is. So in this case, my x-intercept is at 0.36. So I'm also going to include that point, even though it's not one of our data points, but just to kind of help me draw the curve of best fit on there. Okay, so we get something that looks kind of like this, going in that direction. All right. Part C says, what are the x and y intercepts? So we just looked up the x-intercept. I'll flip back to that in a moment. But again, when we are talking about log equations, there are no y-intercepts. And the x-intercept, I can't remember what it was. It was 0.3 something, 0.368. So my x-intercept is at 0.368 and 0. If we're describing the end behavior, so this is an increasing logarithmic function, which means that we are starting from quadrant 4 and going to quadrant 1. Now, just like with the with all of the other ones that we've done, there we are going to be looking for specific information. Part E says state the domain and the range. So if we were stating the general domain would be from 0 to infinity. The range goes from minus infinity to infinity. But there is one thing that I want to point out is because we are talking about a specific example here, there are going to be restrictions on our domain and our range. So for example, if we're talking about the age of a tree, age can't be a negative number, which I mean is already reflected in our domain, but the age of the tree is also not going to be infinite. So if a question does ask you about restrictions, you could say that the x values cannot be infinite because age cannot be infinite. Okay, so that kind of restricts our domain. And we could make the same argument for the range too. The tree is not going to be growing and growing and growing to infinity. Like, how many infinitely tall trees do you see out there? So my y values also cannot be infinite. And we did also say that our range goes to negative infinity. Also, they cannot be negative in this case because trees cannot grow negatively. We're talking about the height of a tree. That's what my y values are. So in this particular context, again, if a question is asking you about any restrictions on the domain and the range, those are some restrictions that you can talk about. Talk about how age cannot be negative, age can't be infinite, as well as height. Height can't be negative, height can't be infinite. Now we talked about this on the previous page. Is it increasing or decreasing? It is increasing. Now part G, H, and I are questions that looks like we are going to be using our line of best fit, our regression equation. So part G says, what was the average height of the trees at 1.5 years of age? So years are my x values. So what I'm going to do is on Desmos, I'm going to enter x is equal to 1.5, and I'm going to solve for y. So let's go ahead and switch back to Desmos. So I have x equals 1.5 entered. I get this intersection point that appears, and the height of the tree is 8.576. So we get a y value of 8.576. Again, make sure you are answering to at least 2 decimal places. But we aren't just interested in the y value, we're interested in answering the question. So it would be 8.576 meters because we're talking about the height of a tree. Now part H is asking the height of the tree at 20 years of age. So again, we're going to enter x is equal to 20. We're going to find what the y value is there. So when we enter x is equal to 20, the intersection point there is 24.39781. So y is equal to 24.39781. So let's go ahead and flip back to our notes again. And again, we're talking about the height. So we could say 24.39781 meters. Again, you can round it to 2 decimal places, but just make sure that you are accurately rounding. Is this prediction realistic? Well, do trees grow to be 24 meters high? I mean, yeah, I would say that they do. I don't know the natural growth of this particular tree, but there are trees that can grow to be 24 meters. So I would say yes, it is realistic. But if you can argue that it's not realistic, I mean, by all means, go right ahead. There's one more part to this which says, based on your observations of this data, what would you predict to be the average height of a mature Higgin cherry tree? So I'm not sure exactly what it means by the average height. So let's go ahead and take a look at our graph and see if we can figure out some kind of information. Because like we were saying about logarithmic functions, they do tend to kind of even out after a while. And I mean, even when we start looking at 30, 40, 50 years of age, there isn't that much growth that is happening. So I would say maybe, I mean, this is more of a, there's no exact answer to this, but you could see that between 20 years of age and 50 years of age, the tree only grows 5 feet in this case. If we keep going here to between 50 and 100 years of age, we don't even hit 35. So this is more of an observation question than an exact answer question. I mean, again, I don't know how long these trees tend to live, but I would say around 25 to 30. Also, I realize that these the numbers are in feet. They're not in meters. So I'm going to change all of these to feet here. Okay, and then I would say because the curve flattens out as the age gets higher. All right, so again, this is more of just how do you interpret the graph. There's no necessarily correct answer to this. It does require some critical thinking that you have to put into it. And that's about it for regression. So there are some practice problems that come after this. So make sure that you know, again, how to make a table of values and find the regression equation. But then also make sure that you are interpreting the questions in context, and make sure that you are giving your answers in context as well with the appropriate units attached to it.